Good morning. Next portion is long transmission lines. In the last class, we have seen how to model a medium length transmission line as it's a T equivalent or pi equivalent circuit. And compared with the medium length transmission line, in case of long transmission line, we'll be considering the continuous variation of the line inductance and capacitance or the line parameters. Because in the medium length transmission line, whether it is represented as T model or pi model, we are assuming that the line parameters, the inductance and capacitances are assumed to be lumped at certain positions, either at the end of the transmission line or at the middle of the transmission line, depending upon the model under consideration, whether it is nominal T representation or nominal pi representation. So, in order to analyze the long transmission line, we have to consider the continuous variation of the line parameters. So, this is the model of a transmission line, and all the transmission lines whose length is greater than 160 kilometers will be considered as long transmission line. And here you can see that in order to analyze the network, that means if we have to find the analysis purpose, we consider the long transmission line is made up of infinite number of small segments as shown in this figure. Here you can see that we are considering the transmission line at a length of x or we are considering the voltage and current at a point x from the receiving end. That means if you consider the distance from the receiving end, this is the receiving end, and let this be the distance x, and the voltage at the point x from the receiving end is capital V in this case, and the current at that point, that means the current at this particular point is I, and we are assuming that the series impedance per Z is the series impedance per unit length, and here it is small z, and this is small y is the shunt admittance per unit length, and we know the length of the transmission line is small l in this case. So the total impedance, you know that the impedance per unit length is small z. So you have the length of the transmission line as L. So the total impedance Z will be Z into L. That will be equal to capital Z here. And Y is equal to Y into small y into Z, where small y is the shunt admittance per unit length. And when multiplied with the length of the transmission line, it will give you the total shunt admittance. Now we are assuming that the capital V is the voltage at a point x from the receiving end as shown in this figure, and the current at this point. And you can see that as you will have infinite number of capacitors connected in between these 2 points, because you can see that actually the transmission line will be something like this. A number of capacitors will be there, and when there is a change in the length of the transmission line from x, for example, if you consider the transmission line up to here, and if you consider the length up to x plus delta x, actually you have some capacitors connected here, because the capacitances are there, infinite number of capacitances are there as per our assumption. So you can see that if I is the current at this point, you can see that there will be some current flowing, or there will be some charging current flowing through this capacitor. That means current at this point will be more than this, because IR, anyway you can see that IR will be always less than IS, because IS will be equal to IR plus whole the charging currents here. So if you consider the current if you consider the current at a distance x from the receiving end, say at a point x here, and if you consider the length x plus delta x, actual current will be I plus some delta I will be there, because there will be some more capacitors connected here, and there will be charging current, and you have to consider that charging current also. And you can see that if you consider a small length of the infinitesimally small length of the transmission line added to the transmission line under consideration, that the added to the length of the transmission line under consideration, that is x here. So we are considering this more portion, and you can see that let its impedance be length be delta x. So its increase in the impedance will be, say, small z into delta x. That will be the increase in this when we increase the length from x to x plus delta x, increase in impedance will be small z into delta x. Similarly, the increase in the admittance will be small delta x into small y. That will be the increase in the admittance. So from this you can see that this is the increase in the impedance, and you can see that the current, there will be a drop across this impedance. So additional voltage drop will be I into this impedance. So I into small z into delta x will give you delta v, and that is the formula we have used here for the derivation. Delta v, the change in the impedance, or the change in the voltage delta x from the original length x. We have considered up to this point x, and up to here you have x plus delta x. So because of that change in length, the additional voltage drop will be, here you can see that VR will be, VR is given by, or Vs, the sending end voltage is given by VR plus the drop across all this impedance. So the drop across this additional or this infinitesimally small portion of the transmission line will be delta V, that will be equal to I z into delta x. And here you can see that the change in length is infinitesimally small. So we are assuming that in order to approximate this equation delta V is equal to I z delta x, we are assuming that there is no change in the current, because the change in length is very small. So the impedance, the change in voltage will be I into the change in impedance, that is z into delta x. That is how we are getting this. Similarly, on the same lines of argument, you can see that if you change the length of the transmission line under consideration from x to x plus delta x, the change in the admittance will be delta x into y. So the change in current will be, we know the current is given by V into the admittance. So this is the change in admittance, means the change in current will be delta I, which is equal to V into this admittance, y into delta x. Here also we are assuming that since the change in length is infinitesimally small, we are assuming that the voltage at both the ends is same. That is why we are taking V here. So we have these two relations, delta V is equal to Iz into delta x, and delta I is equal to Vy into delta x. And from the definition of the derivatives, as delta x tends to 0, delta V by delta x will be equal to dV by dx. Similarly, as delta x tends to 0, delta I by delta x will be equal to dV by di by dx. So from here, as delta x tends to 0, we get a relation dV by dx is equal to Iz. Similarly, from here, as delta x tends to 0, we get the relation di by dx equal to V into y. That means we have these two equations, dV by dx is equal to Iz and di by dx is equal to Vy. And from here, Vy, from here if you differentiate, once again with respect to x, here we get d square V by dx square. If you differentiate this expression with respect to x, we get d square V by dx square, that will be equal to di by dx, because that is the variable here and z is constant. So we have di by dx into z, and di by dx is this expression. So we get d square V by dx square, that is equal to di by dx into z, and di by dx is Vy. So we have Vy into z. We get this relation. D square V by dx square is equal to z into y into v, this relation. Now if you solve this differential equation, here you have d square V by dx square is equal to Vzy. So the resulting differential equations will be d square V by dx square minus Vyz equal to 0. Here the variable is V, so it can be written in the form d square, if capital D square minus d square minus zy into V is equal to 0. This is an operator, d square minus d square minus zy into V, or d square minus zy of V is equal to 0. And in order to solve such a differential equation, you have to find the characteristic equation or solution for the characteristic equation will be d square minus yz is equal to 0. Now we have an equation d square minus small yz of v is equal to 0. So in order to find, anyway, here in the solution for this differential equation, there won't be any particular integral, and its solution will be easily obtained if you find the solution for the characteristic equation is d square minus yz equal to 0, which give d is equal to say yz, d square is equal to yz, or d is equal to plus or minus root of yz. So its solution will be equal to v is equal to, it is of the form c1. This can be considered as plus or minus m. So its equation will be c1 e raised to mx plus c2 e raised to minus mx. You might have studied this in mathematics. So instead of m, you have plus or minus yz. So the equation will be v, the solution will be v is equal to a constant, then e into root of yz into x plus b into, b is a constant which we have to evaluate, and e raised to minus root of yz into x. This is the solution for this differential equation d square minus yz into d square minus yz of v is equal to 0. Now we have the solution for the differential equation b is equal to a e power root of yz into x plus e raised to, plus b e raised to minus gamma. This is actually m plus or minus m into x. And now if you define ZC is equal to the characteristic impedance, ZC is equal to root of Z by Y. We are defining it like this. Here you can see that Z is the impedance per unit length and Y is the admittance per unit length. So 1 by Y will have the unit of impedance. So Z into 1 by Y, that is Z by Y, will have the unit of impedance. So this variable or this impedance Zc is known as the characteristic impedance, which has the unit of impedance or O, and omega, which is defined by omega is equal to root of yz. Here you can see that it will be a complex quantity which has a real and imaginary part, and it is in this part gamma is known as the propagation constant. Now if you substitute these variables, here we have defined Zc is equal to root of Z by Y, which is known as the characteristic impedance, and gamma, which is equal to root of Yz, which is also known as the propagation constant. Now if you substitute these variables in this solution, here we have the solution for the differential equation a e raised to gamma x. The root of yz is defined as gamma, that is how you are getting it as gamma x plus b e raised to minus root of yz into x, and root of yz is a gamma, so we have this relation. Now if you put the initial conditions, for the initial condition x is, we are considering the length from the receiving end, so x will be varying from the receiving end. So as x equal to 0 means the voltage will be equal to, you can see that when x is equal to 0 means we are considering this point, that means v is equal to Vr, and when x is equal to L means we are considering the voltage at the point when x is equal to L will be Vs. So those are the initial conditions. So if you substitute initial conditions at x equal to 0, we have v is equal to Vr, because when x equal to 0 we are at the receiving end, so v is equal to Vr and capital I, current is equal to IR. And when x is equal to L, we are at the sending end. So if you substitute x equal to 0 here, v, when x equal to 0 you have a into e raised to 0 plus b into e raised to 0, that is Vr is equal to a plus b. We get this equation, Vr is equal to a plus b when we substitute the values for x. That is those are the initial conditions. And here when you substitute I is equal to IR, you have this relation. Before that we have to evaluate this. We have this expression v is equal to a e raised to gamma x plus b e raised to minus gamma x, and we have this relation dv by dx is equal to iz. here you have this expression dv by dx is equal to iz. So if you substitute that here, dv by dx is equal to iz. dv by dx, if you substitute this expression, dv by dx will be a e raised to gamma x into gamma. So that is equal to a e raised to gamma x into gamma plus b e raised to minus gamma x into minus gamma. That will be dv by dx. So you can take gamma outside and you have this expression a e raised to gamma x minus b e raised to minus gamma x, and that is equal to iz, that is equal to I into z. So I will be equal to 1 by z into gamma into dv by dx, and this expression dv by dx, you have this expression. So from here iz is equal to gamma into this expression a e raised to gamma x minus b e raised to minus gamma x, and gamma is, we have already defined gamma as root of yz. So here I is equal to gamma by z into a e power gamma x minus b e power minus gamma x, like this, and gamma is equal to root of yz divided by z will be equal to root of y by z, and here you can see that this is 1 by zc. By definition, root of z by y is zc, so root of y by z will be 1 by zc. So if you substitute this here, that means this expression gamma by z is equal to 1 by zc. So you get the expression for I as I is equal to 1 by zc into a e power gamma x minus b e power minus gamma x. That is the expression here. This is actually 1 divided by x. This is not I, it is 1 by zc a e power gamma x minus b e power minus gamma x. Now if you put the initial conditions in this expression, when x is equal to 0, I is equal to IR. So you get this expression IR is equal to 1 by ZC. When x equal to 0, you have a into e raised to 0, that is a minus b. So you have this expression. So when you put the initial conditions, you have these two expressions. VR is equal to a plus b, IR is equal to 1 by ZC into a minus b. From here you can evaluate a. From here you get IR ZC is equal to a minus b, and you have an expression a plus b. Now if you add these two, you get 2a is equal to VR plus IR ZC. So a will be equal to VR plus IR ZC by 2, and b is equal to, if you subtract from this equation from this, so you get VR minus IR Z by C will be equal to 2b. So VR minus IR ZC by 2 is equal to b. Now if you substitute these variables, actually these are the unknown constants in the expression for the solution of the differential equation. V is equal to a into a. This a and b are the unknown values, and that we have evaluated from the initial conditions. So the expression for v is equal to, so the solution for the original differential equation will be equal to v is equal to, that means the voltage at a distance x from the receiving end, that will be equal to v equal to VR plus IR ZC by 2. This is the a e raised to gamma x plus b e raised to minus gamma x. Similarly, I is equal to 1 by ZC a e raised to gamma x minus, this is the expression for b e raised to minus gamma x. So, and the ZC and ZC, which is defined as Z by Y, which is known as the characteristic impedance, and gamma is the propagation constant. Here you have the explanation for ZC and gamma the propagation constant, both are complex quantities, and you can see that Z is the series element of the transmission line parameters, that is R plus J X form. So we have R plus J omega L. Similarly, we have seen that in case of admittance, the shunt parameters we are representing as admittance, and actually if there is some loss component, it will be a parallel combination of resistance and capacitance, because the admittance we are considering the shunt elements we are representing in terms of admittance. That is why we have taken y is equal to j omega c after assuming that there is no loss component. But if you had a loss component here, the admittance part of that or the conductance will be small g. So conductance is given by 1 by R, where R is the resistance. And in order to find the parallel combination of this, and if it is represented as the admittance, it will be 1 by R plus 1 by Xc. So that will be 1 by 1 by R plus 1 by Xc. And this 1 by R is G, and this is the imaginary part of the admittance. Admittance will be G plus J omega C. Initially we had assumed that there is the transmission line is lossless or there is no resistive component as part of the shunt element. So G was we have taken in the analysis for the median length transmission line, we have taken G is equal to 0. So in case of a lossless transmission line, G will be equal to 0. So in case of a lossless transmission line, the impedance, there won't be any current flowing through this. That means this resistance will be infinity. So no current will be flowing through that. So 1 by of that infinity will be equal to 0. That is how we are getting G is equal to 0 for a lossless transmission line. And this lossless transmission line, we are considering in this analysis, we are considering the shunt component of the or the resistive component of the shunt element as infinity. But if you consider the series element R plus J XL, so this is the series element, so you have a component, a resistive component and an inductive component. So if this transmission line is lossless, means this is a series element, so you have to consider R is equal to 0. So for a lossless transmission line, Zc is equal to root of Z by Y, and this is the expression for Z if you consider the per unit resistance per unit length of the transmission line and inductance per unit length of the transmission line. And for a lossless line, R will be equal to 0 and G will be equal to 0. So this will be this j omega and these two get cancelled, and finally you have Zc is equal to root L by C, where L is the impedance per unit length of the transmission line and inductance per unit length of the transmission line, and C is the capacitance per unit length of the transmission line. And you can see that this expression Zc is equal to root L by C is defined as the surge impedance of the line. And typically for a transmission line, Zc will be approximately equal to 400 ohm. And for a cable, Zc will be approximately equal to 40 ohm. This is a standard value. So sometimes it will be in some of the questions, especially for the competitive examinations, question will be there to pick out the surge impedance of a line or a cable. So it will be nearly equal to 400. Sometimes the value will be given as, for example, 380 and 38. So in that case, this will be representing the surge impedance of the transmission line, and this will be the surge impedance of the cables. Approximately it is 400 ohm and 40 ohm for the cable and 400 ohm for the transmission line, overhead transmission line. And these are the points to be remembered while discussing the modeling of the long transmission line. When dealing with the high frequency source surges, normally the losses are neglected and therefore the characteristic impedance becomes the surge impedance. Because we are considering a lossless line, so R and G will be equal to 0. So Zc will be given by root of Z by Y. And surge impedance loading of a line is the power transmitted when the line is terminated through a resistance equal to the surge impedance. From this formula, you can see that when Zc is equal to, we have the expression for voltage, V is equal to VR plus IR Zc by 2. So if you terminate a transmission line with an impedance equal to Zc, you can see that IR will be, because this is the transmission line and we have the voltage VR here. So if you are terminating the transmission line with an impedance Zc here, you can see that IR will be equal to VR by Zc. So IR ZC will be equal to, this is IR. So IR into ZC will be equal to VR here. So VR minus IR ZC by 2 will be equal to 0. That means the voltage will not have this component. And you can see that if you compare the expression, to compare the two terms of the voltage expression for the voltage, we here you have the this component which has e raised to minus gamma x can be considered as a reflected component, and when the transmission line is terminated with its characteristic impedance, this term or the negative e raised to minus gamma x term will not be there. That means the voltage will not have any reflected component. That is why the the impedance loading of the line is the power, and here you can see that so the voltage, this is the expression for the voltage, this is the incident voltage and this is the reflected voltage. So when the line is terminated with ZC VR minus IR Z by C, this expression will be equal to 0 and the voltage will not have any reflected voltage. And the surge impedance loading of a line is the power transmitted when the line is terminated through a resistance equal to the surge impedance. The approximate value of the surge impedance for the overhead line is 400 ohms and that of the cable is around approximately 40 ohms. The phase angle of ZC for the transmission line is usually between 0 degree and minus 50 degree. A line, this is important, a line terminated in its characteristic impedance is called the flat line or an infinite line. It is important. A line terminated in its characteristic impedance is called a flat line. That we have already seen, because when the transmission line is terminated with its characteristic impedance, you can see that VR minus IR ZC will be equal to 0. That means the reflected voltage will be equal to 0. That is why it is known as, or it is called flat line or an infinite line. The later term arises from the fact that a line of infinite length cannot have a reflected wave. That is the, because there won't be any reflected wave will not be there on the transmission line. So it is assumed to be an infinite line. And the lower value of the surge impedance in case of cables, we have seen the typical value of the surge impedance of the cable is 440 ohm. It is because of the relatively large capacitance of the cable and low inductance of the cables, because here you can see that in case of cable the separation between the conductors are very small compared with the overhead transmission line. So the or the capacitance between the different lines will be higher in case of cable. So the value of the surge impedance will be less in case of cable. The propagation constant omega gamma is equal to alpha plus j beta. The real part is known as the attenuation constant and the quadrature component. Beta the phase constant and is measured in radians per unit length. So this formula you have to remember, and this is considered as the incident voltage, and because this coefficient or the power of E here is positive, and here you can see that this is e power minus j beta x. So this term is termed as the reflected voltage. And in order to calculate the transmission parameters or the ABCD parameters of the transmission line when it is represented, or when in case of a long transmission line, and as in the other cases for the medium transmission line or for the short transmission line, in order to find the transmission line or ABCD parameters, we have to express Vs and Is in terms of Vr and Ir. So Vs, Is will be equal to ABCD, which are the transmission parameters. Then you have Vr and Ir here. That means Vs in terms of Vs will be AVR plus BIR. Similarly, Is is equal to CVR plus DIR. And we have the general equation V is equal to VR e power gamma x. This expression we have, and with these identities, if you rearrange the expression for V in this case, here you can see VR, you have VR here, and here you have VR into e power alpha x plus e power j beta x. Similarly, here you have e power minus alpha x and minus j beta. So it will be alpha plus j beta x here, and here it will be minus alpha plus j beta x. So the coefficient of VR here, or you can take VR outside, and the expression will be, here you have e power alpha plus j beta x, and here you have VR into e power minus j beta x. So e power minus, because we are considering only the coefficient of VR, e power alpha minus plus j beta x by this 2. Here you have VR by 2, and here also you have VR by 2. So it is something like this. So this is e power, this is of the form e power theta plus e power minus theta by 2. So it will be cos term e power gamma x plus e power minus gamma x by 2. That is the expansion of cos h gamma x. Gamma is alpha plus j beta x, as we have seen. And if you compare the coefficient of IR ZC, this will be sin h gamma x. So we can be written as VR cos h gamma x plus IR ZC sin h gamma x. And this formula we have already seen, I is equal to 1 by ZC VR into e power, and this is e power gamma x minus e power minus gamma x by 2. Similarly, this expression is there, and this corresponds to sin h gamma x, and this corresponds to cos h gamma x. So I can be written as VR by ZC sin h gamma x plus IR cos h gamma x. So, and if you input the initial conditions, because when x is equal to L, you have, when x is equal to L, that is we are measuring the distance x from the receiving end. So when x is equal to L, the length of the transmission line means V will be equal to Vs, the sending end voltage. Similarly, when x is equal to L, I will be equal to Is. So in order to get an expression for Vs and Is in terms of the length of physical parameters of the transmission line, that is the length of the transmission line, and in terms of VR and IR, the receiving end voltage and current, we can put these initial values. That is x is equal to L, where V is equal to Vs and I is equal to Is. So we get these two expressions, and this set of equations can be compared with this. So this will be C, and this will be B, and this will be D. So this is A, this is B, this is C, and this is D. So that is how we are getting these transmission line parameters A, B, C, D as this. And you can see that in case of a transmission line, the two-port network or the network will be symmetrical as well as reciprocal if you check these conditions. A is equal to D, that you can see, because A is cos h gamma L and D is cos h gamma L. And AD minus BC, if you substitute AD minus BC A into this, that is AD is cos square gamma L minus BC, this HC and this HC gets cancelled, and you have cos h square gamma L minus ZC sin h gamma L by sin h gamma L by ZC. So you get cos h square gamma L minus sin square h gamma L, that is equal to 1. That means the representation is valid, and it is a reciprocal and symmetric network. And in case, if you represent the transmission line as in terms of its transmission line parameters, and if you have two cascaded transmission line connected like this, cascading means the end of one of the transmission line will be connected at the starting end of the other transmission line. So you have two sections. This is section 2, and this is line 1 or section 1. So the output voltage or the receiving end voltage of the section 1 will be the sending end voltage of the section 2, and the receiving end voltage of the second section will be the VR here in this case. So this is Vs in case of a cascaded two networks, or when you have two transmission lines cascaded like this. And if each individual transmission lines are represented by their ABCD parameters, you can simply multiply these matrices in order to get the ABCD parameter of the combined matrix. So if you have three transmission lines connected in cascade, you have to multiply the three ABCD parameter matrices of the individual networks, and you will be getting the ABCD parameter of the resultant network. So this you have to remember. If you have two individual networks or two individual transmission lines whose parameters or whose ABCD parameters are known, then if they are connected in cascade or in tandem, you can get the equivalent ABCD parameters of the combined network by simply multiplying the matrices. And the remaining portion in this module 2 is the Ferranti effect. Ferranti effect means when a long transmission line is there which is operating under no load or very or light loaded condition, and if the when the length of the line is very high, usually you can see that the charging current will be higher. The receiving end voltage, sometimes the receiving end voltage is greater than the sending end voltage. This is known as the Ferranti effect. When a long line is operating under no load or light loaded conditions, the receiving end voltage is greater than the sending end voltage. This is known as the Ferranti effect. Generally, the receiving end voltage will be less than the sending end voltage, but in particular cases that you have to remember, for long and lightly or unloaded transmission line, lightly loaded or unloaded long transmission lines, the receiving end voltage will be sometimes greater than the sending end voltage, and that effect is known as the Ferranti effect. And a simple explanation of the Ferranti effect can be given by approximating the distributed parameters of the line by lumped impedances. Sometimes question will be there to explain how the Ferranti effect is happening. In that case, you have to draw this equivalent circuit of the network. Here actually we are assuming that the line capacitance is lumped at the end of the transmission line. It's an approximate analysis, and you can see that in this case, when there is no load on the transmission line, you have only the charging current IC flowing through this. That means there is no receiving end current. IR is equal to 0 in this case, or IR will be very small compared with the capacity of the transmission line or compared with the charging current of the transmission line. And you can see that if you take VR as reference, you can see that this current IC, because this is the voltage, VR is taken as the reference phasor, and you can see that IC is flowing through. Well, at this potential you have VR. So the current through this capacitor will be voltage across the capacitor is VR. So the current through the capacitor, it should lead by an angle 90 degree. So this will be the direction of IR. This is IC. This is VR, because this capacitor is connected across the voltage VR. So IC, it will be leading by an angle of 90 degree. And when this IC is flowing through this, you can see that there will be a drop across this resistance, which it will be equal to IC into R, and you can see that this drop will be parallel, or it will be in phase with the current flowing through this. So this IC into R will be drawn parallel to this, because this is the direction of IC. So IC into R will be in this direction, and the drop across the inductor will be lagging by an angle of 90 degree with respect to the current, and this is the direction of the current. So the voltage across the inductor, it should lag by an angle of 90 degrees. So it will be something like this. That is why it is written, or it is drawn like this. It is lagging by an angle of 90 degree with respect to the current. Now VR plus the drop across this. This is VR, and the drop across this is the phasor sum of these two. ICR plus ICX. This is ICR is the drop across this resistance, and ICX is the drop across this inductance. So this will be the drop across the Z here, if you consider these impedances or line impedance as Z. So this is the drop across the line impedance, and this is the receiving end voltage. And you can see that VR plus this line drop. VR is this voltage, and this is the line drop. That will be equal to Vs, the sending end voltage. And you can see that magnitude wise, VR is greater than Vs. So this is a simple explanation of the Ferranti effect.